All right, so this is a tutorial on aerosol mixing state, metrics, measurements, and modeling. My name is Nicole Riemer from the University of Illinois at Urbana, Champaign, and I have with me my co-author Andy Ault from the University of Michigan. So we want to start with a global view of the atmospheric aerosol. And what I'm showing here is a movie that was produced by a group at NASA, and it shows the global burden of different types of aerosols as they are transported around the globe. And so what you can discern from this picture very easily is there's dust coming from the desert of the Sahara being transported over the Atlantic Ocean. That's the orange color. There is aerosol coming from biomass burning activities in the Amazon and in Central Africa. There's pollution coming off the industrialized region of the Earth, North America, Europe, and Asia. And there's also sea salt aerosol being emitted by the oceans in the areas where we have high wind, which is the Southern Ocean here, and the westerlies in the Northern Hemisphere. And aerosol particles affect our lives in many ways. I'm just showing a few examples here. So we see the severe pollution episodes that they have in Asia. Here's an episode in Beijing a few years ago. This picture shows the same scene taken across the street and on a nice day on the left here and on a very polluted day on the right. Then aerosols affect our lives. A few years ago, there was a big volcanic eruption in Iceland, which grounded many flights. Aerosols affect our lives when you think about wildfires, which they happen very frequently now. Here is shown an example from wildfires in California that can be seen from space. So we see the biomass burning plumes emerging here from areas with fires going over the ocean. And we care about these aerosols. One of the reasons is there are health impacts. But then another reason is they are very relevant for climate. And the chart that is shown here shows different agents in the atmosphere that exert a radiative forcing. So on the top here are the well-mixed greenhouse gases, and when the bar goes to the right, it means they are warming the atmosphere. So CO2 exerts a warming effect on the atmosphere. And then as we go down here and we see the aerosol impact, the aerosol radiation interaction and the aerosol-cloud interactions, we see the bar is going to the left, meaning aerosols on the whole exert a cooling effect on the climate. And so what we also see is there is a huge error bar associated with these impacts, meaning that we don't understand them as well as we do the effect from other greenhouse gases, for example. And overall, aerosols are known to have a very uncertain impact on climate. So we know it's cooling overall, but we don't know exactly what the magnitude is. And so with this, I'm turning over to Andy.
So as Nicole made the case, it's very important to understand where particles are coming from and what they're made of if we want to think about their broader scale impacts on things like climate and health. And so we included this image right here as a way to give us an idea about sort of how we can think about aerosols evolving in the atmosphere and what we mean by this whole term of mixing state. So in this idealized image you can see here, we start over on the left side of the screen. I'm highlighting there some particles that may be emitted in a remote region like dust, showing how they can mix with different anthropogenic pollutants as they move over an urban area, both gaseous as well as particle. And so new types of particles getting emitted that we're showing here are in, say, orange or purple or green and black, in addition to our particles that were transported there, are more grayish brown particles. We also can have things that complicate mixing state, such as the uptake of secondary species. And so a classic example of this is secondary organic aerosol or things like ammonium sulfate formation in the condensed phase. And so what do we mean by that? If we look at the yellow that we have circling some of these particles, that gives us an idea that it's a secondary species. And in some cases, we've seen particles that have become stuck together as well, such as, say, this purple and brown particle right here. So we've moved from an environment on the left where things are very separate to an environment where things are more mixed together. And we'll talk about how we can describe these different types of regimes on the next slide. And as we continue then out over the ocean, we have more and more aged particles, meaning that we have more and more secondary species in yellow. But as we go over the oceans, we also have the input of new sources, primarily from the ocean, but also from things like ships. And this continues the evolution of our mixing state. And so overall, what we're really trying to make clear is that we don't just need to know the snapshot of what's getting emitted initially, but we need to understand how things change over the course of their time in the atmosphere. And so mixing state is really our way of moving to more of a video if we're thinking about what aerosols are doing versus just having a picture at the beginning of when they're emitted. And so how can we think about representing this? If we look at the images that I'm showing you here, this is an electron microscopy image in the upper left, as well as elemental maps surrounding it for different things, such as dust particles, salt particles from the ocean, or sea spray aerosol particles, or biological particles. And if we look at which elements are located within the different particles, you'll see these do not all have the same composition. Our salt particle, for example, if we look at this magnesium and sodium map, shows a number of differences here between, say, the salt particles and the dust particles. Our biological particle down here in the lower right has a lot of carbon in red. And if we look at markers that are typically associated with secondary species like sulfur in red here, or nitrogen in green, you can see that they are not evenly distributed between all the particles or within each of the different particles. And so our goal from this is to think about how can we describe this in a way that's going to allow us to understand the impacts that this has on climate and health, because there's, if you take in a deep breath of air, you're breathing in a million different particles. How do we represent this in a way that's reasonable? And so the two most common ways that this has been represented, going back to the 70s, is through what we call an external mixture over here on the left, where we have a single component within each particle, say ammonium sulfate here in, or hydrophobic organic material in blue, sulfate as well. So we have those two. And if you put blue plus green together for an internal mixture, then this assumes that every particle has the exact same composition, in this case 50% ammonium sulfate, 50% hydrophobic organic material in each particle. And these are the most common ways these are represented within models. But they're not the same. And they don't necessarily represent the real world. So when we look over here on the right, we can see things like a particle that has an ammonium sulfate core with a hydrophobic organic coating. We can see things where they're homogeneous mixing within a single particle, or we can have more complex structures like what we would call a partially engulfed particle up here in the upper left. So if we think about why, again, should we care about this, we think back to things like climate, like clouds. And so in that sense, we could think about for each of these three very different scenarios, how many of them are going to be able to form cloud droplets? And so if we look at each example here, you're going to get a different number of particles that have been able to become a cloud droplet if they're exposed to a certain supersaturation. And so because of that, if we are using in a model to try to predict mixing state, external mixing versus internal mixing versus a more complicated representation, we may get very different answers. And so that's a fundamental reason that we wanted to do this tutorial, was to try to get this point across. And so when we go on to measure aerosol mixing state, it becomes really challenging because they're really complex, and we can measure a lot of different things. We can measure what elements are present in each particle. We can measure what molecular composition we have, what molecules are there. We can measure what's on the surface versus what's in the bulk of the particle, both from an elemental or a more molecular perspective. And we can look at things such as surface structure or surface tension to try to understand how things will go between gases and particles, as well as things such as an internal structure or inclusions. So with all of these, we have a number of different tools at our disposal, and this is something that my group works on a bit, looking at electron microscopy, mass spectrometry, vibrational spectroscopy, surface-sensitive spectroscopies like X-ray photoelectron spectroscopy, and other groups do things like some frequency generation to understand surfaces. So if we try to summarize all of these, you can see here we have put on two different axes. We have species coverage, so how many different species are we measuring, and then what's our chemical detail. And we've broken this down by sort of different categories I showed you on the previous slide of electron microscopy with X-ray spectroscopy, vibrational spectroscopy with optical microscopy, mass spectrometry, or more indirect methods, and whether or not the method measures individual particle by particle, or whether it, say, collects an ensemble average, such as a bulk filter. So with that, we can think about how all of these different methods are able to measure different sizes of aerosols. And so for this figure, we show things, this is from a review in Analytical Chem in 2017, showing moving sort of from less chemically complex approaches, such as the SP2, which looks at soot particles, to more chemically specific information like the bioaerosol sensor, the WIBs, scattering and absorption measurements, electron microscopy with X-ray spectroscopy, and more vibrational spectroscopy type information, including surface sensitive spectroscopy. So with that, I'm going to turn it back over to Nicole to talk about how we can think about these complexities in a model scenario.
Yeah, okay, so by now we know why we care about aerosol particles. That aerosols are these complex mixtures of different chemical species, and we have all these sophisticated tools to probe aerosols and the associated mixing state. On a more theoretical basis, how can we think, or how can we quantify the fact that aerosol populations and particles are these mixtures? And so one of our tools is thinking about particle diversity. And so it's written out here how we actually mathematically define it, but on a more visual basis. So what we basically define is this diversity index that we can assign to each particle. And the important thing to know here is it's based on the mass fractions of different chemical species in the different particles. And so a particle that consists of just one species would get assigned a diversity index of 1. That's pretty intuitive. And so as we add more species, meaning we are making the particle more and more complex, this diversity index increases. So it goes from 1 to 2 if the 2 species are present in equal amounts, and to 3 if they are again present in equal amounts, if we have 3 different species, and so on. So this can go to even larger numbers. And so that's a way how to characterize how complex each individual particle is. How many species are involved in making up one individual particle. And then we can take, if we know mass fractions of individual particles, we can take them and average them over the whole population, which gives us an important metric, and that's this d alpha metric right here. And then, so particles exist in these populations. Another important number to know, not only how, on average, how complex each individual particle is, but also how different particles are from each other. And so then we can combine those two metrics to our so-called mixing state index chi. And so chi varies from 0 to 1, and 0 would correspond to a completely external mixture that Andy already introduced in a couple of slides before, where each particle is made out of a single species, going to a completely internal mixture where all the particles look the same, and they're basically, their composition is equal to the bulk composition of the whole population if I was just simply averaged all the mass contributions out. And so this brings us to an important point, and that is the point that was made in the 70s, that the same net composition of an aerosol can be caused by a large variety of different internal distributions of the various compounds. So that's basically this issue. You can have the same amount of red, yellow, and blue, but those 3 different species can be distributed in a very different way over the population. And so the extremes are external and internal mixtures, but there are many different states in between. And that is important if we think about macroscopic impacts such as CCN properties or scattering and absorption, and even health impacts. So now that we have a more fundamental definition of what mixing state is, these quantities can be measured in the field. So this shows an example of a field study that took place in France, in the area of Paris. And they were determining these mass fractions of individual particles that I mentioned before to construct this mixing state metric. And so they did this for a whole month, and you can see how the mixing state of this aerosol population changed from more internally mixed at the beginning of the campaign to episodes where it was more externally mixed, and going back and forwards over the course of an entire month. And so this has been done for a few studies in different areas, and the publications are cited in this corner right here. Now, as we now move on to common aerosol modeling approaches, this whole mixing state issue causes a big challenge, right? So in common aerosol models that are used in global climate models or regional air quality models, we represent aerosols as distributions, just like shown on the left and on the middle here. And that glosses over a lot of details. So what we assume here is that within each size range, so if this is size and this is the amount or the number concentration of particles, we assume in each size range the particles look all the same. And from the real measurements that Andy has shown before, we know this is not true, right? And so to replicate this more realistically, we could use more sophisticated modeling approaches that are also computationally more expensive. On the right here shown a particle resolved model that literally resolves individual particles and how their composition changes over the course of the lifetime in the atmosphere. So as I go from the left here to the right, these modeling approaches become more accurate, but also more computationally expensive. Now, how do we figure out how important mixing state is? And so one of the approaches is the so-called closure study approach. And the way this works is, so if we stick to the example of cloud condensation nuclei concentration, if we wanted to figure out how many particles can form cloud droplets under any given conditions, we could figure this out by measuring those cloud condensation nuclei concentrations. So there are methods to measure these directly. Or what we could do, we could measure the size distribution and composition, apply a model for CCN, so feed this into our model for CCN and calculate the CCN concentration. And in that calculation, I have to assume what the mixing state is, right? Because just from measuring size distribution and composition, this is not directly known. So I have to assume, are they more externally or more internally mixed? And then I can compare the agreement of the directly measured CCN to the calculated CCN. And then if that agreement is good, then presumably I got the mixing state assumption pretty right. If this is bad, then I might have to refine that mixing state assumption to get a better agreement. And this has been done in many studies. One example is shown here, a paper that came out some time ago in 2008. And so what is shown here is the agreement of measured CCN concentration to model CCN concentration, just in the procedure that I explained before. When they assumed an internal mixture, they were causing a large overprediction of the calculated CCN concentration. When they used a more sophisticated mixing state assumption, then they got a better agreement, but they got a lower R-square value for these comparison from measured to calculated CCN. So that's just showing that it's quite tricky to actually get this right. And another way of figuring out how important mixing state is this benchmark modeling approach. So with the model approaches that I introduced before, we can use like a very high detailed model, run a simulation, calculate cloud condensation concentration using really detailed information about the per particle composition. And then we can compare this with results from a more simplified model, and we could see how well they agree. And it has been shown in our studies and other people's studies as well that as we go to a more externally mixed aerosol population, assuming internal mixture leads to quite large errors here. So on the x-axis, this is the result from many simulations where we graph the results as a function of the mixing state metric that I introduced before. And the errors are on the order over 100% if we assume an internal mixture where it actually is rather externally mixed. And with this, turning it back over to Andy for our summary.
So Nicole's really nicely laid out the fact that we have evidence that if we make simple assumptions and ignore these mixing state factors that we're talking about, that we are likely going to end up with a scenario where we're going to have errors in our work. So it's worth taking a moment to kind of step back and think about, how can we represent these different particles? And so, we used earlier when we were defining these diversity terms and thinking about the different components, we used the pie chart that Nicole has over here on the left. If we think about aerosol mixing state, we mean this for an entire population. So one thing if there's a key takeaway, so you don't have a mixing state of just one particle. You need to have a whole population of particles to have to be able to characterize, a mixing state. And so, you can think of that as sort of having a series of these different pie charts over here, as we referred to before. And so if we want to relate this back to how it's often represented in models at the moment, we can think about that internal or external definition that was given before. And so that would fall into this category, where we have the category where we have an internal mixture on the left. Everything's essentially the same. And whereas on the right, we have these different particles, each of which has a very different composition. And so this fits into this overall idea of chemical mixing state. But as I showed you from those electron microscopy images earlier, this is even too simplified to represent reality in some sense. And so there we can think about things such as, the fact that you never really do see a, Pac-Man type particle in the atmosphere. All of these particles have different distributions of species within each particle. And so for the exact same pie chart up here on the upper portion, we can have, all of these different morphologies, kind of the soot fractal aggregate, inclusions, a series of core shell particles. And so we've been trying to come up with how do we describe this so that we can eventually move even further with the modeling that Nicole has described in terms of thinking about the physicochemical properties, because each of these particles chemically has the same components, but physicochemically is very different. And so if we then want to take that the logical step further in terms of thinking about what that means for mixing state, what we are describing next is a physicochemical mixing state, where it's not just the pie charts of composition, but also thinking about how the species are distributed as well as their other properties. And so this is a place that things are going to head in the future, which really is going to help bring measurements and models together. So when we think about what does mixing state mean overall, first of all, we need to ask the question, does it even matter? And the short answer is yes. And the longer answer is it depends on the conditions, and that we need to improve both measurement and modeling tools to really be able to quantify those effects. And we've tried to give just a taste of how that's being done in the atmospheric community at the moment over the course of this tutorial. And so with this, we can continue along sort of an axis that we're showing here from that analytical chemistry review that we had before, where we start with either an internal mixture here with this mixing state parameter chi equal to 1, so fully internally mixed on the upper portion, or something that's fully internally mixed as shown in the lower left here. We can then start thinking about things like the physical properties and the chemical mixing state about how things are divided. And if we put it all together, we end up with the physicochemical mixing state. But we need to integrate better between measurements and models in terms of making the measurement output something that modelers can use. We need to do a bunch of modeling testing, as well as we need to think about how we can integrate different measurements, because these are complex measurements and each individual measurement is often somewhat different. So with that, we think there's a lot of work still to be done in this area, but we hope that you take away from our tutorial today a sense of where the state of the art is with respect to mixing state and where there's still room to continue improving in the future. And so with that, I want to make sure to acknowledge our collaborators from the University of Illinois, Jeff Curtis and Matthew West, as well as Rebecca Craig from the University of Michigan. And this work was funded by National Science Foundation, Environmental Protection Agency, and the Department of Energy's Atmospheric Systems Research programs. And we should mention that the PART-MC model that Nicole has developed is available on GitHub, as well as these other locations below. And so with that, we thank you for your attention. We hope you've taken away something from this. And we, of course, if anyone has any further questions and would like to get in touch with either of us, we'd be happy to talk about mixing state for hours on end if folks would like to. So have a nice day, and we thank you for your time.